Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Materials Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. Now let's just get started on our set of questions for today's session. Okay, so question 1 says to draw the Lewis structure for hydrogen peroxide. It also asks what is the weakest bond in hydrogen peroxide, and hydrogen peroxide is sold commercially as an aqueous solution in brown bottles to protect it from light. Calculate the longest wavelength of light that it has sufficient energy to break the weakest bond in hydrogen peroxide. Okay, so first let's draw the Lewis structure of hydrogen peroxide. And to do so, we're first going to calculate the total number of valence electrons in the molecule. Okay, so hydrogen has one valence electron, and there are 2 hydrogen atoms, so we multiply this by 2. And in the case of oxygen, there are 6 valence electrons, and we also have 2 oxygen atoms, so we would just multiply this by 2 as well. Okay, so 12 plus 2 is 14. So we have 14 valence electrons. So first we're just going to draw our oxygens with a single bond. And then each of those will have a single bond to hydrogen. And from here, we just fill out all of the lone pairs on the oxygens. And if we count out how many I've drawn so far, we have 2 electrons in each bond. So that is 6 plus 8, so that is 14. So this is our final Lewis structure for hydrogen peroxide. Okay, so the second part of the question says, what is the weakest bond in hydrogen peroxide? Okay, so hydrogen is it is the smallest element on the periodic table. So I'm just going to write that oxygen atoms are much larger than hydrogen atoms. So therefore, the intermolecular distance in a bond containing hydrogen and oxide is much smaller than the bond between the 2 oxygen atoms. So the longer bond, which is the 2 oxygen atoms, is the weakest. So the smaller bond you have, the stronger bond it is. So since the 2 oxygen atoms have a longer bond, this will be the weakest bond in hydrogen peroxide. So now let's do part C of this question. We need to calculate the longest wavelength of light that has sufficient energy to break the weakest bond in hydrogen peroxide. So to do this question, let's first recall this energy equation, where energy is equal to Planck's constant times the speed of light divided by your wavelength. So we can rearrange this equation and solve for wavelength. So if we solved for wavelength, it would be hc divided by E. So now let's just plug in all of the values. So Planck's constant is 6.626 times 10 to the negative 34 joules times seconds. And the speed of light is 3 times 10 to the 8 meters per second. Okay, so now for E, we need to find the bond enthalpy of the two oxygen atoms. So I'm just going to look it up on Google. So the bond enthalpy between two oxygen atoms is found here, so it is 146 kilojoules per mole. And before I before I do any calculations, I want to make sure that all my units should cancel out. So instead of kilojoules per mole, I'm going to convert this to joules just by multiplying it by 1,000. So now if we multiply this through, we end up getting around 1.36 times 10 to the negative 34. And the units, if we see here, is meters times moles. So now I have an answer that is in meters, but because it is in moles, I want to get rid of that and try to figure out the energy to break the weakest bond in hydrogen peroxide. So I'm going to multiply by Avogadro's number to get the units that I need. So Avogadro's number is 6.023 times 10 to the 23 . So let me just write mole in. And the units for Avogadro's number, I'm just going to say atoms per mole. And now our units for moles will cancel out. And then we have our answer in meters, which is 8.2 times 10 to the negative 7 meters. And if we converted this to nanometers, then it would be the same as 820 nanometers. Okay, so let's see what the junior tutor said. Hydrogen has 1 valence electron, while oxygen has 6. Hydrogen follows a duet, while oxygen follows an octet. Okay, so they have a more accurate Lewis structure, but it is pretty much the same. And B, oxygen has a bigger radius than hydrogen. We have either hydrogen or hydrogen-oxygen or oxygen-oxygen bonds to choose from, and from the nature of the atom's radii, the hydrogen-oxygen bond will be shorter and thus stronger. The weakest bond should be the oxygen-oxygen bond. Okay, so for part C, they wrote the bond enthalpy of the oxygen-oxygen bond and got 146, and they showed their energy equation. Okay, so they plugged it in to the equation, multiplied that value by Planck's Avogadro's number, and also got 820 nanometers. So this solution is correct. Okay, question number 2 is to name the following compounds. So here we have 2 phenyl groups, and they all have different substituents. So this is a benzene ring, which is a 6-membered aromatic ring. And before we start naming, we want to number all the carbons in the ring. And we want to make sure that we have the lowest number possible at the end, and that our most important group, so in this case it is the alcohol group, so we want to make sure that this group is on carbon 1. So if our alcohol group is carbon 1, if we wanted the smallest amount of numbers, we're going to go counterclockwise, making this bromine on carbon 2 and the second bromine on carbon 4. Okay, so now that we numbered our benzene ring, we can start to name it. So first we're going to specify which carbons the bromine atoms are on. So on carbon 2 and carbon 4, we have 2 bromines, so I'm going to put the prefix di and then bromo. And our parent is benzene, which can also be called like a phenyl group. So the parent name is phe, and then we are going to end it in all, which already tells us that carbon 1 has the alcohol group. So the name of this compound is 2,4-dibromophenol. So now we can do a similar approach to our second compound. Now let's number again. And we also go counterclockwise since the methyl group and this iodine group are right beside the alcohol group. Okay, so again, we are going to specify which carbon all of the other substituents are on. So this is an iodo group, and this group is called a methyl group. So if we were to do it in alphabetical order, the iodine group would be named first. So on carbon 3, we have our iodine group, so 3-iodo. And then on carbon 2, we have our methyl group. And then again, our parent is called phenol. Okay, so let's see what the junior tutor said. Polysubstituted aromatic compounds are named as follows. First is by identifying the parent that will give the least number of locant to the other substituents. For example, if the aromatic compound has an OH group, the name of the parent will be phenol, or if it has a methyl group as a substituent, the name of the parent can then be toluene. Okay, so that's why our parent was named phenol. And then they just have a lot of different examples of different aromatic compounds. And then starting with this is just an example of their own. So in this case, the parent will be phenol instead of aniline because one of the substituents is closest to the OH group. So if the iodine were closer to the NH2, then the parent would be called aniline. The second is by naming the remaining substituents and assigning them their corresponding locants. Note that the substituent of the parent is always treated as number 1, and the locant of the other substituent should be the least number as possible. So they showed how they would number this particular example. Lastly, finalize the name by arranging the name of the substituents alphabetically, then add the parent name. For the given example, the name of the substituents will be iodo and amino. Therefore, the name of the compound is 5-amino 2-iodophenol. Okay, so now they get into our question. So they said the name is 2,4-dibromophenol, which is correct. And for part B, they said it is 3-iodo-2-methylphenol. Yep. So this solution is correct. Okay, so question number 3 says to give the full electron configuration of rubidium in the ground state, provide the orbital diagram of the last subshell with electrons. Provide the quantum numbers for the last electron. Okay, so first let's write out the electron configuration of a rubidium atom in ground state. So first we need to divide our periodic table into the different sections. Of the orbital shells. So this column is the S block, and this green is the P block, and the middle is the D block, which are the transition metals. And lastly, the last 2 rows is the F block. So starting from hydrogen, we're going to move left to right across the periodic table, writing the row number and then the block letter. But when we get to the D block and the F block, or the D block, the number is going to be the row number -1, and in the F block, it's going to be the row number -2. Okay, so let me write out an example. So for rubidium, rubidium is found here, atomic number 44. So starting from hydrogen, we write 1s2, and then to the next row it is 2s2, and then moving over to the P block is 2p6, and then continuing on we have 3s2, 3p6, and then once we get to the 4th row, the D block has a lower energy than our S block. So we're just going to write our D block before we write our S block. So this makes it 3d10, and then 4s2, and then 4p6, and then 5s1. So this is the ground state electron configuration for the rubidium atom. So the second part of the question says to provide the orbital diagram of only the last subshell with electrons. So our last subshell is the 5s subshell. So let's write our orbital diagram box, and I'll label this as the 5s subshell. And there's only one electron, so I'm just going to draw a single electron pointing up. And now we just need to provide the quantum numbers for this last electron. So since it is in like row 5, our principal quantum number, which is n, will be equal to 5. And our L value is based on the block letter. So for example, if you're in the S block, your L value is 0, the P block is 1, the D block is 2, and the F block is 3. So I'll just keep this up. So since we're in the S block, then our L value would then be 0. And because our L value is 0, our ML value can only be 0 as well. And for the magnetic spin number, since the electron is spinning upwards, we're going to write positive half. If it was spinning down, then it would be negative half. Okay, so this is 3A. So now let's see part B, which is to give the full electron configuration of a zinc 2+ ion. Provide the orbital diagram of the last subshell with electrons, and then provide the quantum numbers for the last electron. So it's a similar question to the first, but instead we deal with the cation, zinc. So it had a 2+ charge. Oops. It had a 2+ charge, but first we're going to write the electron configuration of a zinc atom in its ground state. So it's the same process. Zinc is found right here, atomic number 30. And let's start to write down its electron configuration. So 1s2, 2s2, 2p6, 3s2, 3p6, and then 3d10 I'll write first. And then I'm going to write 4s2. Okay, so now if we have a zinc that has a 2+ charge, this means that 2 electrons were removed. So the electrons that are going to be removed are the ones from this 4s subshell. So now we can write our new electron configuration. It's just going to be the same thing, except it's going to be missing the last 2 electrons. Okay, so now we're going to draw the orbital diagram for the last subshell. So in this case, it is the 3D subshell. So now let me draw out the boxes. So the D subshell is able to hold 5 electrons. 10 electrons, sorry. And these numbers range from -2 to +2. And if we had 10 electrons then the whole thing would be filled. So let me show how one would fill in the electrons. We have them all spinning up first, and then when we start to fill in the rest is when we would spin down. Okay, so this is our filled 3D subshell. And now let's write out the different quantum numbers. Okay, so since we're in the 3D subshell, our n value is equal to 3. Our L value, according to the table that I wrote out, will be equal to 2. And then for the last electron, our ML would then be equal to positive 2. So we're talking about this electron right here. And since it is spinning down, then our MS value would be negative half. Okay, so now let's look at part C. Circle the orbital diagram that has the correct arrangement of electrons in the orbitals. What kind of subshell is this? So they have different options. So looking at the first one, everything is spinning up, even the second electrons that were written. So the first option is wrong. And the second option, they started to fill in electrons going down, even though the whole subshell wasn't filled with electrons spinning up yet. So the second option's wrong. And the third option, everything is filled except for one of the first boxes. It doesn't have an electron spinning down, so that's why this one is incorrect as well. And our fourth option is actually the correct one. We can double check this because our last option has 2 filled boxes with the whole subshell, the rest of the subshell being empty. So we know that the fourth option is correct. Fourth option. The one where they filled it in correctly, so you can show the electrons spinning up. And then for the last two is when you would start to fill in the electrons going down. So the type of subshell is a 3D subshell, or just a D subshell in general. Similar to our example in the previous part of the question. So now let's see what the junior tutor said. Rubidium is in group 1, period 5, therefore it has 1 valence electron in the 5s orbital. So the full electron configuration of rubidium is the following. Yep, so that's correct. And then they drew their diagram. N is equal 5 because it's in energy level 5. L is equal to 0 because it's in an s orbital. ML is equal to 0 because the s orbital can only have one orbital. And ms is equal to plus half. The electron has an upspin. Yep. And for zinc is in group 12, a transition metal in period 4. So a neutral zinc atom will have the electron configuration. So this is the short form, which is good as well. Argon 4s2 3d10. The neutral zinc atom loses 2 electrons from the 4s orbital. So the zinc 2 plus ion has the full electron configuration of the following. Yep, so that's correct. And then they wrote out their 3D subshell. N is equal to 3, L is equal to 2, ML is equal to 2, and ms is equal to -½ because it's spinning down. And then lastly, option 4, which is D, a D subshell. All d orbitals have to be occupied first before electrons pair up. Paired up electrons must have opposite spins. Yep, so that's a good summary of the rules. So this solution is correct. Okay, so question number 4. The highest mass peaks in the mass spectrum of Br2 occur at mass over charge 158, 160, and 162. The ratio of intensities of these peaks is approximately 1:2 to 1, and bromine has 2 stable isotopes, bromine 79 at a 50.7% abundance, and bromine 81, which is a 49.3% abundance. Part A, what molecular species gives rise to each of these peaks? And part B, explain the relative intensities of these peaks. A hint is to consider the probabilities of each atom combination. Okay, so for part A, I'll just summarize that 3 mass peaks correspond to different combinations of isotopes of bromine. So when we have an isotope, this is when our atom has the same number of protons, but a different number of neutrons. So in the case of bromine, when we have like bromine 79, that the mass of it would be around 79, and the mass of this bromine 81 is around 81. So this is why, this is how they got their names. So they differ in the number of protons. So, I mean, the number of neutrons. So this is why they have a different mass. So we can have different combinations of the bromine ion, or different combinations of the isotopes of the bromine. So for example, when the mass peak was equal to 158, so if we divide this by 2, you'll notice that we have 2 atoms of our bromine 79 isotope. So 79 times 2 is 158. Similarly, we can do the same thing for the second peak at 160. This can be a combination of 1 atom of the bromine 79 and 1 atom of the bromine 81. And lastly, when we have the mass peak at 162, this can be the 2 atoms of bromine 81. So 81 times 2 is 162. Okay, so these are all the different peaks. So now let's do part B of the question. Explain the relative intensities of these peaks, and we need to consider the probabilities of each of the atom combinations. So we know that the ratio of the peaks is equal to 1 2 to 1. So let's look at the probability of each atom combination. So the probability of having two atoms of the same, so I'm going to put an asterisk when we have two of the same. The probability is 25%. And the reason for this is because we have a 50% chance of a specific isotope and another 50% chance that it's going to be the same. So that's why the probability is 25%. So we can show this as 0.5 times 0.5 is 0.25. So now let's talk about the option if we have one of each. I'm going to put an asterisk on our middle option. So the probability is 50%. So this corresponds to our 2 in the ratio. And this is because since we have a 100% chance of a bromine atom, and then we have a 50% chance that it is the other, the opposite one. So it doesn't matter which one you start with, you still just have a 50% chance that it's the opposite one. So this kind of explains the relative intensities of the peaks, how you can have 1 to 2 to 1. And now let's see what the junior tutor said. The peak at 158 is caused from the bromine molecules made of 2 bromine 79 isotopes. Peak at 160 is caused from bromine molecules made of 1 bromine 71 and bromine 81 isotope. And lastly, the peak at 162 is caused by 2 of the bromine 81 isotopes. Okay, so they drew out a table for part B, just showing how, oh yeah, this is a helpful way of doing it as well. It's kind of like a Punnett table from biology. You can show the different combinations. So when we have 2 of the same, it's a 25% chance. So 279 bromine isotopes, 281 bromine isotopes is 25%. And the percentage of having a molecule made up of 179 bromine and 181 bromine is 50%. So the 50% is highlighted in the bold, and that's an easier way of showing the probability of the isotopes. So this solution is correct. Okay, so question number 5 is to draw the correct product for the following Diels-Alder reaction. Okay, so first let's go over what a Diels-Alder reaction is. This is when you have a conjugated diene. So this is just a fancy way of saying like two double bonds that are a bond apart. So when you have a conjugated diene and a substituted alkene, which can also be referred to as a dienophile, they come together to form a cyclohexene derivative. Okay, so let's try to write out the mechanism that would occur in our question. Okay, so this is the first reactant, and the second, and it looks like this. Okay, so I'll show how the movement of electrons would occur for this reaction. So one of the bonds from here will come in and attack the double bond, moving them here to form a double bond on this carbon instead. And then this comes in and attacks right there. And this leaves us with our product. So this part stays the same. But when we get to this part of the compound, we have a newly formed bond that kind of brings the two together to form a cyclohexene derivative. Okay, so this is, you can see where the two kind of like came together. And then this is our new double bond that was formed here. And yeah, that's our product for this Diels-Alder reaction. Now if we see what the junior tutor said, Diels-Alder reaction is kind of cycloaddition reaction that involves a diene and a dienophile. In here, two sigma bonds are formed and two pi bonds are formed. Oh, two pi bonds are lost to form a substituted cyclohexene. And this happens via a concerted process. Okay, so they show dotted lines as to where the new bonds will form. Okay, so they have your diene and your dienophile, and the substituted cyclohexene that is formed. And this is our question, and you can see that they got the same product. So this solution is correct. Okay, so question number 6. What is the Lewis structure for selenium tetrafluoride? So first, let's just find out the total number of valence electrons for this molecule. So we have selenium, which has 6 valence electrons. And for fluorine, there are 7. And you multiply this by 4 since there are 4 fluorine atoms. And 28 plus 6 is 34. So now I'm going to draw selenium as our central atom. And then I'll just show all the single bonds to all the fluorines. And I'll also fill in all of the lone pairs on my fluorines as well. So if I count out how many electrons I've drawn so far, with each bond containing 2 electrons, I only have 32 out of the 34. So for my last 2 electrons, I'm just going to put them on my central atom. Okay, so let's see what the junior tutor said. They have a step-by-step guide. Okay, so they started off with the skeletal structure. And they kind of explain how they draw all the electrons in. And they got the same Lewis structure as well. And they also calculated formal charge, which is good. Oh, well, they explained how one would calculate the formal charge. And for this neutral molecule, it should add up 0. So the solution is correct. Question 7, draw the Lewis structure for this bromine difluoride that has a negative charge. So first, let's find the total number of valence electrons. Bromine has 7, and fluorine also has 7, and we multiply it by 2 since there are 2 fluorine atoms. Then we're going to add an additional 1 electron because we have a negative charge, and we should get around 22 valence electrons. So now we have bromine as our central atom. Then I'm just going to draw 2 single bonds to the fluorine and show all of the electrons. So if I count out all the electrons I have so far, I only have 16 out of the 22. So since each bond contains 2 electrons. So because I only have 16, I need 6 more. So I'm just going to put them all on the central bromine atom. So now I'm just going to calculate for formal charge. So formal charge is equal to the number of valence electrons minus the number of non-bonding electrons minus the number of bonding electrons divided by 2. So first, let's do the fluorine. So each of the fluorines are the same. They both have 7 valence electrons and 6 non-bonding electrons. And there's only a single bond, each containing 2 bonding electrons. And then we just divide that by 2. So the formal charge on both of the fluorine atoms is just 0. For the bromine also has 7 valence electrons, And this bromine atom has 6 non-bonding electrons, and it has 2 single bonds attached to it. So there are 4 bonding electrons in total, divided by 2. So 7 minus 6 minus 2 is -1. So then this is where our negative charge would be on the bromine atom. And our junior tutor did the same thing. They calculated valence electrons and got the same Lewis structure as I did as well. So this solution is correct. Okay, so question 8. In liquid methanol, which intermolecular forces are present? So let's show structure of methanol. So if we recall, the oxygen is much more electronegative than carbon and hydrogen. So we're going to have a non-zero dipole moment going towards the direction of the oxygen. So this means we have a partially positive side overall and a partially negative side. So this can tell us that dipole-dipole moments or dipole-dipole interactions will occur because the positively charged side will be much more attracted to the partially negative side of another methanol molecule. And similarly, we can have so let's say we can show how this oxygen-hydrogen bond will still contain partially positive and partially negative side. So this partially positive side will be attracted to partially negative side of another methanol molecule. So this is called hydrogen bonding. And lastly, we could also have London dispersion forces. So this is present in all molecules, and it's when there's a temporary attractive force that results when you have 2 adjacent atoms that occupy like different positions that make the atoms form temporary dipoles. So this takes place in all of the molecules. So therefore the answer is is option A. And the junior tutor said the following. The 3 most common types are London dispersion, dipole-dipole, and hydrogen bonding. Okay, so then they give a brief explanation about what each one means. So it all looks correct. And then they drew out the structure of methanol and how there's a dipole-dipole reaction because of the polar bonds in the molecule. Okay, so this solution is correct. Okay, so question 9. What is the molecular geometry of beryllium dichloride? So first, let's find the total number of valence electrons for this structure. So our chlorine atom contains 7 valence electrons, and since there are 2 of them, we multiply this by 2. And beryllium only has 2 valence electrons. So if we were to draw out its Lewis structure, we would just have our single bonds to the chlorine, and if I showed all the lone pairs on chlorine, then we already have our 16 electron count. So now let's use the VSEPR table to show the molecular geometry. On our beryllium atom, we have 0 lone pairs, and we have 2 bonded atoms. So if we look at our VSEPR table, when you have 0 lone pairs and 2 bonded atoms, the molecular geometry and also the electron geometry is linear. And we can say that this is sp hybridization. The bond angle is 180 degrees. And the junior tutor said the same thing. So this solution is correct. Now I think we have time for one more quick question. With what mass of lead nitrate with a molar mass of 331.2 grams per mole is required to react with 1.25 liters of 0.55 moles per liter solution of potassium chloride? Okay, so they already gave us a balanced chemical equation, so this will help us answer the question. Okay, so our potassium chloride solution had a volume of 1.25 liters and a concentration of 0.55 moles per liter. And we also know that our lead nitrate has a molar mass equal to 331.2 grams per mole. And we're trying to find its mass. So step 1 is to first find the number of moles of potassium chloride. So we do that by multiplying our concentration and our volume. So the concentration was 0.55 moles per liter, and the volume was 1.25 liters. So this cancels out our liters and tells us that we have 0.688 moles of potassium chloride. So now step 2 is to use the mole ratios to find the number of moles of the lead nitrate. So if we know that the number of moles of the potassium chloride is 0.688 moles, then we can multiply this by the ratio in which it reacts with the lead nitrate. So I always put what I'm looking for on the top. So we have 1 mole of lead nitrate that reacts with 2 moles of KCl. So you notice that the KCl moles will cancel out, and we get 0.344 moles of the lead nitrate. So now step 3 is to find the mass. So if we recall that mass is equal to the number of moles times molar mass, we can just plug in our values, so 0.344 moles of the lead nitrate times its molar mass, which is 331.2 grams per mole. So our grams is 113.85 grams is needed. Okay, so let's see what our junior tutor said. They wrote out everything that was given, found the number of moles of potassium chloride. Yep. And then they did the mole ratios to obtain the equivalent moles of lead nitrate and got 0.3438. And lastly, they solved for mass by multiplying the number of moles times the molar mass. Okay, so this solution is correct. Okay, so those are all the questions for this session, and if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. If you'd like to submit a question of your own, then check out the links in the description. And also don't forget to share this video with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.